Good afternoon. So we are here for the third lab session, and I just want to cover some of the points that we discussed in the earlier class, because you're going to be using those concepts in today's lab. So we basically looked at systems which have more than one lens in them, and we also said even a single lens, if you can't ignore the thickness, you can think of it as having more dimensions to it, and you approach those ideas through these planes called the principal planes. So we arrived at the way to calculate the locations using matrix methods. Okay, I need to correct one thing. So this distance from the vertex is the back focal plane. Let me just rewrite that. And this distance from the principal plane, this will be your effective focal length. So I had said that reversed. Okay. Now we have used this matrix method to arrive or calculate the locations of these planes, and the usefulness of these planes is that I can now treat this entire system. It doesn't matter how many lenses or optical operations it has in it. I can now treat it in the same way I would treat a thin lens, only making measurements now from the principal planes rather than from the vertices. Okay. So when I think of it now, how did we use the thin lens earlier? We had some rays we could trace through that thin lens very easily, and there are similar rays you can trace through a system which has many optical operations in it and which you analyze through the principal planes. So I want to introduce those different rays to you, or points, different rays, different points to you, and for today's class I will introduce 6 points of interest, 6 points, some which seems familiar or similar to what you have done in the thin lens, and we'll just see those definitions in terms of the thick lens system. So there are 3 pairs of points: the focal points, the principal points, and the nodal points. You already are familiar with the first 2 pairs. But let's just run through those definitions again. So you know now how to calculate where the principal planes of a system occur given a system. So in this case you have obviously a very thick lens, not just a thick lens, it's a fat lens, right? And you have the location of the front focal plane, and how do I use that? You can see from this diagram, any ray coming from the focal point, in our thin lens understanding we say it emerges from the system parallel to the system, right? Anything, if you had an object point at the source, you would send it out parallel after the lens, and that's what you can see over here. What is very clearly demarcated, let me draw that for you, is, say you take the first ray, it is traced from the object point to the first surface of the thick lens. In this diagram it very clearly shows you the refraction that happens within the thick lens, right? And then it bends such that it emerges parallel. The advantage of having the principal plane or the defined for us is I could so for us the trick would be, if I have a thick lens and I have a ray coming like this, how do I know where to draw it parallel over here? That's the difficulty. If it's a thin lens, the ray, the point at which it hits the lens, it's at that point that I draw it out like this. With the thick lens, I can't do that because it has bent and traveled at an angle within that thickness, so it emerges at a slightly different height. And knowing where the principal planes are allows me to actually draw from the point at which the ray emerges, because I will draw a straight line starting from here. I will draw this line straight all the way to the principal plane, and then I will bend it and draw it parallel to the optical axis. That's not really what's happening, but the principal plane allows me to do this. You know why? Because we've gone through that derivation. So within the thick lens system, that's not really how the ray is traveling, but what's important to us is we know how it traveled up to the surface, and this allows us to draw accurately where the ray emerges after the second interface. As you can see, these regions are being drawn in dashed line because they allow us to draw the final ray, but that's not actually what's happening within the surface. You'd have to then take the refraction at those points into account. But we are avoiding doing that exact refraction at each surface and just using this concept of the principal planes to accurately draw the incident ray and draw the exit ray. Okay? So that should get clear to you. And you can see here, this is the front focal distance, and as I said, it is from the vertex. The effective focal length is from the principal plane. And similarly, you have for the rays that come in parallel, they will get focused to the back focal plane or the back focal point, and the distance from the lens to this point is the back focal length, and the distance from the second principal plane to this point will be the effective focal length. Okay? So, principal points, they are basically the points where the principal plane crosses the optical axis. This you have seen in the morning class. Okay. We also have a pair of points called the nodal points. Now, we know in a thin lens system, if you had a thin lens drawn like this, if you were tracing a ray through the center of this lens, doesn't matter what angle it's coming in, it would go through the center undeviated. That's what we said for a lens going through the center of our thin lens. So, whether it comes in at a shallow angle or at a larger angle, it always goes like a straight line through the center of the lens. I can't do that anymore if I am considering a thick lens, but I can trace a ray coming so that it is traveling straight. It hits some point. If I were to continue it straight, but that's not what's happening, it's going to refract. That ray goes through the center and then refracts again. So, these points N and N dash, they are called the nodal points of the system. What can I say about this ray A and B? A and B are parallel rays. So, these rays, the incident ray and the emerging ray are parallel, and they have gone through the center of this lens. If, however, I were to trace them undeviated, they would appear to come from two different points on the optical axis. We call those the nodal points. Okay? And this is the equivalent of the ray going through the center of the lens in the thin lens case. Okay? Now, what am I saying here? I am saying A and B are parallel, but I could always have a thick lens where the radii of curvature R1 and R2 are not equal. So, let us say R1 and R2 are not equal. May not be evident in this figure, but let us say I had a case where R1 and R2 are not equal. I am still going to say the nodal rays are parallel before and after. Why do you think that is so? How can they be parallel if the radii of curvature are different? Do you expect the angle of refraction here to be the same as the angle of refraction here? Let us say this is N1, N2, N1. Do you expect the angle of refraction to be the same if R1 and R2 are not the same? I am asking this because it brings across a very, very important point. When I say parallel, we are talking about the angle with respect to the optical axis. If I talk about what's happening at this interface and what's happening at this interface, of course, at those points I am going to apply Snell's law. And Snell's law is always applied, the angles you measure are applied with respect to which direction do you measure angles with respect to? Normal to the surface. So we are not saying that the angles are the same angles when I consider the refracted angles. But remember, your refracted angle was always made up, we could always draw it if we had a curved surface like this and we had a ray coming through like this after refraction. And if this was the normal to the surface, this was the optical axis, this is the angle of refraction. This angle is not the same as the angle in the object space. What we are saying is this angle is the same, right? So that's a distinction over there. When we say the emerging ray is parallel to the incident ray, so the ray emerging from this thick lens system is parallel to the ray incident on this thick lens system. The rays that go through the nodal points are going to be parallel. This only means that we are saying this angle is the same in both cases, not the angle of refraction and the angle of incidence. Okay, so this is with respect to the optical axis. It's a if you understand this point, it really goes a long way in understanding how these rays are defined, okay, and how you can therefore trace them through a system. Okay, so this is every system, of course, will have two nodal points. Okay, and I didn't spend any time on the focal points. The focal points you are clear with. So we have the principal points, the focal points, and the nodal points. Okay. Now, if I take a simple thick lens, what do I mean by a simple thick lens? I'm talking about a single lens but has thickness. So not a combination of lenses or not even lenses plus distances. That's a compound lens. Here I cannot neglect the thickness of this lens, but it is a single lens with one medium kept between two curved interface, or between two interfaces, at least one of which has curvature. Okay. This lens itself, you can calculate the principal planes. Using exactly the same method we used for this thick lens, you will be able to find out what is the ABCD matrix, and then using those values of A, B, C and D, you will be able to calculate the locations of the principal planes. For a simple thick lens, the principal planes, a rule of thumb is that the planes will be separated by roughly 1/3 the thickness of the lens. So if in this, as I have drawn here, this is the thickness of the lens, and let us say it has thickness T, the separation between the principal planes will be roughly T by 3. Okay, it's a rule of thumb. If you have a lens which has a planar surface, one of the principal planes is always going to lie at the lens vertex. Okay. If you have a biconvex lens, they are going to be symmetrically located, and you can always use matrix calculations as we did in the morning to find out the location of the principal planes. So I have some images here for different simple lenses, so simple thick lenses, and for each of these cases the principal planes have been located. So you can see in the first picture you have a biconvex and you have symmetrically located principal planes, and the distance between them is roughly 1/3 the overall thickness. Here you have, it's still biconvex, but there's more curvature, it's approaching plano-convex because one surface is almost planar, and you can see the location, it's no longer symmetrically located, the principal planes have moved and one is getting almost to the vertex. When you actually take a plano-convex lens, so that means one surface is flat, the other is curved, you can see one of the principal planes is located over here at the vertex. For this meniscus lens, we call this a meniscus lens when both surfaces have curvature with the same sign. This is a meniscus lens. For such a lens, you can see that the principal planes lie outside the lens. And this is the last point I have put here. Depending on your system, the principal planes could lie anywhere. And if you are trying to make a measurement or needed access to the principal planes, it could be sometimes that they lie within an optical lens, within some part of your system. It may not be very accessible. You may not be able to make a measurement easily from that point, right? So, if for some reason you need to access the principal plane, you have to look at your design and make sure that the principal planes are at accessible locations. So, I won't run through the lower set of figures. They are again for more concave lenses, and you can again see how these different points are validated if you look at different types of concave lenses. Okay. Okay. So, with that, so with this background now, you are ready for today's lab exercise. And today's lab exercise is, in the last exercise you said you learned how to design a lens with a very specific focal length. In today's class, you are going to now analyze thick lens systems. Okay. So, I just want to bring out some points in OSLO, and then you will be ready to. So, I have opened OSLO. I have a couple of rows here, and let us just say I add some. So, I am going to put a simple lens, a simple thick lens. Now, right now, and let's solve. So, I am solving the axial ray height. I want the image plane to be at where the axial ray height crosses is 0. So, that in other words, the ray crosses the image axis, and I want to see this surface so that we can see that. Okay. Now, you can see the effective focal length here. That is what is shown over here. Now, you know this is the distance from the second principal plane to the image point, to the focal point. But in this case, your lens has 0 thickness. So, if you look at the distance over here, I have solved for where the ray height goes to 0. So, that is from the vertex. This distance gives you the distance from the vertex of the lens to where the ray crosses the axis. This gives you the effective focal length, which is from the principal plane to where the ray is focused. But in this case, these numbers are identical because the lens is a thin lens. Now, let us say we go and give this lens some thickness. Okay. The moment you do that, these numbers are going to change, right. This is the distance from the surface. This is still the distance. What has not changed, what actually would have changed this, you have changed the system because you have changed the thickness. So, the location of the principal plane is going to change, but you have now the effective focal length measured from the second principal plane, and this is the distance from the vertex of the lens. And so, now you have a difference in those numbers. Okay. Now, this is a very simple system. You could always have a more complicated system, and you can always, and you may not always be looking at you may not always have a parallel set of rays coming in. Your rays could be coming in from somewhere else. So, if you want to look at the location of a principal plane, you need to go to setup and look at this. So, this gives you PP2 is the second principal plane, and this is the distance from the second principal plane to the image position. Okay. So, you get that information from this command here. Okay. Is there something else? Yeah, another point that I want you to think about. In one of the earlier lab classes, we asked you to find out, or maybe it was the last class, you were asked to find out the focal length or design the system to have a specific focal length, and you were asked to use an operand. Which operand were you asked to use? The PU operand. What is the PU operand? PU is an angle. Angle of what? It's the axial ray. So, I can define it at any interface, and we say, we are saying choose. So, what did we do? We went to generate error functions, aberration operands. We wanted PU, so we changed the weight of this to 1, and then if you choose this and you choose some parameter as a variable, OSLO will try to minimize this to 0. Here we didn't want the angle to be 0, we wanted the angle to have a certain value. So, you add whatever or subtract whatever needs to be, so that that total sum goes to 0, right. So, you are controlling the angle. So, now it doesn't matter when I am trying to get the focal length of a system, I am trying to design the focal length of a system. It doesn't matter whether I use the PU operand or the effective focal length operand if I am designing a thin lens. The moment I am designing a thick lens, does it not matter? Can I use either PU or effective focal length? Is it exactly the same thing? You say no, it's not the same thing, and of course I am going to ask you, why is it not the same thing? You are correct, it's not the same thing. Why is it not the same thing? Go and think about what is the difference between using the PU operand and using the effective focal length. How that understanding means you have really understood your chief ray, your axial ray, and your principal points. Okay. So, I want you to think about that. That's a question I am leaving you with, and play around with OSLO if you need to help you answer that question. Is designing a lens with a specific focal length the same? Can you say the procedure to design a lens with a specific focal length the same whether I use the PU operand or the effective focal length operand? And if not, what's the difference between these operands? See, when I go to operands, I don't know if you noticed, when I go here, I can use this, but there's also an effective focal length over here, right. And I did not ask you to use this last one because I wanted you to understand how I use the axial ray. I wanted you to use the axial ray and figure it out. But I could, in fact, you might think that I might want to use the effective focal length, but I want you to think about it and tell me why. Okay. Another point, just this is more out of how to use OSLO, and it's easier to use OSLO. When you're first setting up your operands, you go through the process that I just did. So, you go to optimize, generate error function, aberration operands. When you do this, it will always clean the slate. Anything you had defined earlier is cleared, and it gives you this. Right? So, let's say we choose PU and we want to reduce some aberrations. So, we choose, so we have given all of these weight 1, that means these are the operands we want to work with, you accept this. Now, say you want to go back and make some change, you do not have to go back through that, then you just go to operands and it will give you back those operands with whatever entries you had already made. If you go back the way we had the first time, it will give you a clean slate, everything you have defined would be wiped away. So, if you wanted to add or edit something, you just go back this way, and then you do not have to re-enter all the information, only go make the specific change that you need to make. The effective focal length uses the principal axis. You are saying define or change some parameter somewhere. Yes, so you are attempting to answer the question, right? So, the difference is when I say use the effective focal length, we are saying, say I had chosen curvature of one of the surfaces as the variable with which to change focal length of the system. I am saying change the curvature such that the effective focal length, that the focal point lies this distance away from the principal plane. Whereas when I say axial ray, I am saying change the curvature so that the ray bends such that it crosses the axis at this distance away. Right? They need not be the same thing if the lens is a thick lens, right? Okay, so it's not exactly the same thing. It depends on what you want to do. It depends on what your goal is, but it's not exactly the same thing. Okay. Okay. So with that, you can start today's exercise. Today's exercise is basically working with thick lenses and how you can pull out relevant information about thick lenses from OSLO and how you can design certain thick lenses. Okay.